So hello everyone. So I'm Théo Gnassounou. So I'm a third year PhD student, almost graduating in 1 month. And I will present you the Python package SKADA made for tackling distribution shift in machine learning. And it's a joint work with Antoine Colas that cannot be here today, and Rémi Flammarié just here that will present another package just after. So first, I will introduce you what is distribution shift in machine learning. Okay. So if you're using machine learning, you know that it's a powerful tool. So if we take a simple example, you can classify, for example, apple and pear. So you can take a classifier, train this classifier to recognize if one images can be an apple or a pear. So if you train, and now your classifier is trained, so you can give new sample new images of apple or pear, and it will give you the right label. But sometimes shift happens, so now you can have quick draws of images. So quick draws of pear, of apple or apple, and you cannot be sure that your classifier will give the good labels on these two images, because it's not exactly the same things. And it will be the same thing if you give paintings of pear or apple. So if you train a classifier, you want to deploy it in your area, you want to be sure that your classifier will work properly. So in domain adaptation, we'll suppose that we have different number of domains. So here we have one domain where we have real images of pear and apples, one domain where we have quick draws of fruits, and one other domains where we have paintings. So each of these domains have the same classes in it. So we have pear and apples, but we don't have the same features that describe these fruits. So we have distribution shifts between these domains. So if we train a classifier or estimator on one domain, we cannot be sure that we will have good performances on other domains. And you can have the same problem, for example, in medical analysis, where you, for example, you record a functional MRI of brain. So depending on the subject, the brain structure will be different. So if you train a classifier on only one subject, you cannot be sure that your predictor will give the good prediction for other subjects. Or if we take a new example, if we want to train a car to drive autonomously, if you train the car on clear images, you cannot be sure that it will drive perfectly if there is a foggy, if there is fog or rain in front of the car. So I think it's only 3 examples, but every time, if you don't have so many data, if you train a classifier and you want to deploy it during a long time, the data will change. Everything is moving in the real world, so you cannot be sure that there will never be any distribution shift in your data. And so, what is the impact of distribution shift? So if we take a new example, so you take so 2 domains, one source and one target domain. And here we have just a binary classification problem. So you want to classify the red and the blue dots. So we have the labels accessible in the source data, but in domain adaptation, we'll suppose that we don't have access to the target labels. So here, if we want to train a classifier, we can only train on the source data here. But if we train on the source data, of course, for the target data, you will misclassify half of the points. Everything will be blue here. So there will be a big drop in performance if you have distribution shift between 2 domains. So the domain adaptation tried to tackle this shift, but in practice you can have different shift. So here, if you have the source data here, you can have, for example, covariate shift. So here is just the distribution of the data that changes over domains. So here you can see that the dots for the target data are more concentrated in the middle of the plot. You can also have target shift. So target shift means that the distribution of the labels are not the same. So here we have more blue dots than red dots. You can have conditional shift, so is the condition so it's the condition that's moved. So just here, like everything is moving on the upper right part of the plot. And you have also the subspace assumptions, so which means that in the initial space there is shift. So here in this example, if you just take the source data, you will I think on the above of the diagonal you will say okay it's blue, and at the bottom of the diagonal you will say it's red, but here it's a return, so you will have a 0 of accuracy. But if you find a subspace, so here is the diagonal, if you project everything on the diagonal, you can classify well on the two targets. And so domain adaptation aim to tackle this shift, and there is a lot of Python library to do that, and most of them are not maintained anymore, sadly. And also they are focused mainly on deep learning based domain adaptation methods. So I think it's very useful in a lot of applications, but sometimes you don't really need to have a deep learning framework for your problem. So only shallow methods like random forest, linear regression, or SVC is enough. And that's why we try to implement also a lot of shallow methods. And only adapt library was implementing shallow methods, but was based on TensorFlow, and so and it was not fully compatible with SKADA. So we tried to use Torch and have an API that works fully with SKADA. And also we will talk a bit later on how to validate the parameter with DS scorer, and we are the only library that implements this scorer. And so for all of so domain adaptation will aim to tackle this shift. And so for shallow methods, we have around 20 methods available in SKADA. So for the correlate shift and target shift, you will try to use reweighting methods, so that we put more weight on the source samples that are closer to the correlate to the target data. For the conditional shift, you will use mapping methods that try to move the source distribution to the target distribution. And for the subspace assumption, we use method that aims to find this subspace where there is no shift anymore, and that we can classify well. And in the next, just to explain how you can use SKADA, we'll just focus on the conditional shift for make the thing easier. But if you're interested to know a bit more about other methods, feel free to come to see me after. Okay, so now we'll just go to how you can use SKADA in your pipeline if you want to try some domain adaptation methods. So if you use it as sci-kit-learn, you always have your X and Y. So X will be the data, so the n samples times n features, and you will have your Y, which is each label for each sample. In SKADA, we'll add just a sample domain parameter, which says to which domain belongs one sample. So we just want to be sure that if one dot belongs to source or target domain. So with SKADA, you can create a toy dataset with the function match shifted dataset, and you can, for example, create this plot. And so, as I told you, you cannot have access to the target labels here, so it's always gray. So in the pipeline of SKADA, we try to remove and to mask every time that you want to train an estimator the targets. So to do that, you can use datasets. It's a domain error dataset that we created, and with this dataset, you have a function .pack, and then you can select which domain you want as source, which domain you want as target, and then if you want to mask the target labels or not. And when you mask it, for example, you have this sample domain where you have 1 for the source domain, -2 for the target domain. And when you mask, your Y is, you have the true labels here, but you have a mask labels to -1 for all the target domains. If you don't use this dot pack and you forgot to mask your labels, inside the pipeline of SKADA, we will mask automatically the labels, and we say with an error message that you need to not use it, otherwise you will cheat. Okay, so now what you want to do is to use a method of domain adaptation to tackle this shift. So remember, if we only train a classifier on source data, we'll just misclassify all the target data here. So for example, we can use optimal transport methods, so OT mapping in SKADA. And this method will work in 2 steps. So first, it will adapt the source distribution to the target distribution with a mapping estimation. And then it will train an estimator on the adapted source data. And so this OT mapping is just a pipeline, so with these 2 steps. So OT mapping adapter that will estimate this mapping, and a SVC to classify on the adapted data. And so here, you can, if you want to create a pipeline, you can use the make.da pipeline. So it will be the same as using directly OT mapping as before. And then, as a SKA-learn, you can use the .fit here function, where you give the x, then y as in SKA-learn, but here you have to specify the new parameter sample domain that can, like that, the adapter can understand that there is source and target domain, and in SVC, only the source data will be passed through the SVC to classify. Okay, so if we do the .fit, first you will learn the mapping, estimate the mapping between source and target distribution. So the mapping will be the yellow lines here. If you want to know how you can compute this mapping, just stay just after, because there will be a presentation of optimal transport. And so everything will be clear to how to estimate this mapping. And then after that, the source data are moved, are mapped to the target data, so you can train a new SVC on the adapted source data, and then it's worked properly. And so if you want to score on your data, you can just use again the dot pack methods, but you just want the target here. You don't want to mask anymore because you want the labels to have a accuracy score, and then you can just do your estimator.score with the x, y, and sample domain that only have the target here. Okay. And so then, as you see, all the shallow methods are using a SKA-learn pipeline like that. So it's very powerful because you can do as you did with SKA-learn. So if you want to put, for example, a standard scalar at the beginning, you can just put standard scalar here. And if you do that, you will just first, if you have your initial data, you will just scale your data, and then you can do the same. Estimate the mapping. So it's very versatile, and you can do anything you want. And even more, maybe you saw that there is some shared written just there. So these shared are selectors in our pipeline. That means that both source and target domains are passed through the standard scalar, then on the OT mapping adapter, then on the SVC. But you can change, and you can, for example, use a selector per domain. So which means that you will create 2 standard scalars, one for the source, one for the target. So you can just play with it if you want to do different things. So in this case, you will just scale respectively source and target domain separately. So in this case, you will just cancel the shift here, but it's just a toy data set. So of course the mapping will do not so many things, but it's just to show you how powerful is this DA pipeline. Okay. So as I told you, there is also a side of domain adaptation focused more on deep learning. So that's what we will cover in this section. So if we are going back to the example of pear and apple, if we use deep learning architectures, you will have a feature extractor. If we give a simple example, but we have a feature extractor and then a classifier. the goal of the feature extractor will try to find the discriminative features of peer and apples. So we can say, okay, maybe the color, the texture, and the shape in this example can help to classify these two images. And now, if we give new example coming from the same domain, it's still the same discriminative features that works. But now, if we go for the quick draws, the color and the texture are not helpful anymore. Only the shape can maybe help, but the classifier is trained to detect the color and the texture, so maybe it will misclassify something. And the same thing for the paintings. We still have color, we still have texture, but they're not encoding the same information. So in deep learning GA methods, they will try to learn a feature space that is invariant between domains. So they try to reduce the divergence between the feature space of the source and the target. So basically, how they're doing that? So you will pass through your feature extractor both the source data with the X and Y, and only the data of the target domain, because we don't have the YT here, so we don't have access to the target labels. And so they pass through the feature extractor, so we get the features of both source and target. And then you pass through the classifier only the source features to compute the prediction loss, which can be the cross-entropy loss, because you have your true labels YS here. And then you add, in domain adaptation method, some new loss here that we try to reduce the divergence between the two feature space. And to compute this divergence, you can use different distances, like MMD distance, correlation distance, optimal transport, adversarial methods. You have plenty of methods, all available in SKADA. And just to give you an example of how to use deep learning in SKADA, we'll focus on one method called deepjdot. You will see the name just after, from Damodaran et al. Focus on optimal transport. But with SKADA, if you want to use domain adaptation, you can either use PyTorch, fully PyTorch, or Scorch. We want it to be also compatible with SKADA, also with deep learning. So you can use method with Scorch. So Scorch is a wrapper around PyTorch to have same estimator as SKADA. So if you take, for example, if you just do no domain adaptation, with Scorch, we just create a neural net classifier, then introduce an architecture, give the batch size, give the max epoch, give the learning rate, and then you just do a dot fit on your data, on X source and Y source. But in this case, if you look at the images from the paper deepjdot, so the red dots are for the source and the blue dots are for the target. And as you can see, only all the source dots are clusterized, and there is a lot of target dots that's not clusterized. So if you're doing classification here, it will not work. So we are looking to the t-SNE of the feature space. Sorry, I didn't mention it. But so it will not work if you want to classify the blue dots. And so if you use the deep learning methods, so as I mentioned just before, it will be the same, exactly the same. So if you want to use deepjdot, you just call it here deepjdot. You can put the same thing as before, so the architectures, the batch size, the max features, and you just need to add these two parameters. So the regularization term is just the threshold between the prediction loss and the DA loss. And you put the layer name, which is the output of the layer that you want to perform the reduction of the divergence. So here we want the feature space, so we use the feature extractor outputs. And then, just as before, you can just do the model.fit on X, Y, and also with sample domain. And so you will train your deep learning method to be able to predict properly the classes, but with a feature space that is the same for source and target. And as you can see here, with deepjdot method, the both blue and red dots are clusterized. So now you have a better architecture to tackle the shift with deep learning. And so just in the example just before, you saw that we have a term of regularization, but it's also the case in some shallow methods. So often you will have parameters that you want to tune, as usual in machine learning field. But the problem in domain adaptation is that you don't have access to the target data, and so the question: how can we tune these hyperparameters without access to any target data? So in the literature of domain adaptation, it's not very clear what they are doing. So some paper are validating on targets, so it's not really working because you're saying, okay, maybe I have some targets labels, so it's not your first assumption, so it's a bit cheating. Some paper are saying nothing, they just give parameters without really saying how they tune it. And some of them are proposing cross-validation for domain adaptation or a circular validation here. So we have few papers that are trying to propose domain adaptation validation procedure. So I will just give you one, the circular validation that I think we did a benchmark last year, and we showed that this one was working well for shallow methods. So how does it work? So first you will train, you will have source domain X, Y, and target X. So we'll train a first classifier, your domain adaptation methods, on the source data, and possibly with the target data here. Then, because you train a classifier, you can predict pseudo-labels on the target domain. And then, since you have pseudo-labels for the target, you can do the inverse. So you can train a new classifier FT on the target domain with the YT estimate. And then you can predict with this new classifier on the source some pseudo-labels, some predicted labels for the source. And then since you have the true labels here, you can compute the score. So just first learn on source, then learn on target, and then you can predict. And so it's working well in practice. I think it's the best one. It's not always perfect, but compared to the other DS scorer, it's working well, but it's a bit long because you have to train 2 times. So for deep learning methods, if you have heavy training, it's not the best. But in SKADA, it's very easy to use it. So if you want to use circular validation, you can just call it from SKADA. Then you can, if we take a estimator entropy OT mapping, so it's the same as OT mapping, just we add a new term of entropy regularization. So we have a term of regularization and that we want to train here. So we have these parameters. So you can use the grid source CV from SKA-learn, and just as scoring, you can say, okay, I want to use circular validation. So everything will be done perfectly with SKADA. So you can just do a dot fit and give, of course, the sample domain here that will be propagated around the pipeline, everything. So it's very easy to use DSCore and SKADA. And so it's very powerful, and if you want to do proper domain adaptation with SKADA, it's possible. Okay, so it's the end of the talk. So as you saw, there is a lot of methods implemented in SKADA, both shadow and deep learning methods. All of the methods are in the SKA-learn interface, so it's very easy to integrate in already workflows and pipelines. But it's still the beginning of the journey, so we have a lot of work to do, more methods, more tutorials, and we definitely need some help of the community just to improve. Any feedbacks or contribution is welcome, of course. And if you want, you have so the GitHub of SKADA here. And if you want, we did if you're curious about what are the domain adaptation methods, etc. We did a benchmark of different modalities for domain adaptation just here. So thank you for your attention and don't hesitate to ask questions.
Thanks a lot, Théo. Any questions? We have 5 minutes.
Hello, thank you very much for the talk. It was very good. My question is about calibration. How do you deal, how sensible it is for the domain adaptation when you talk about probability calibration scores?
It's a good question. We didn't, in SKADA you have nothing for calibration. And so I'm not so much aware of what's your on domain adaptation and calibration, so I don't want to say wrong things. I don't know if you have any idea, Rémi? Yeah, but we don't really deal with both domain adaptation problem and calibration right now, but maybe it could be a nice future work, but sorry, I don't have any insight for that.
Any other questions?
Yeah, thank you for your talk. I have a question about possible practical application. One of my cases, for example, is when I have a source data set with a lot of labels that can be easily used for training, and the target is actually the same domain, but with really few labels, maybe enough for validation, but really not enough for supervised learning. And from maybe your experience, did you deal with this kind of cases? Almost the same domain, maybe the distribution of targets will be the different one, but the feature space will be the same, the number of classes, for example, will be the same, and so on.
So what's the difference between your two domains?
The difference will be mostly about the distribution of targets. For example, it will be multi-class problem, and the distribution of probabilities will be the different for source and target domains.
Okay, so you're more like a target shift problem. So
yeah.
So there is in shallow methods, you can use reweighting method that we try to define some distribution and to reweight the samples to put more information of the labels that that's more numerous in the target domain. So you can just reweight the samples like that. You have the same labels distribution basically on your source. In your source domain. So you have some methods available in SKADA for the target shift. And but otherwise, if you have few annotation for in your target data, you can have methods using the target score supervised domain adaptation, semi-supervised domain adaptation. So you can have also this side, but we don't really deal with it in SKADA. But you have some target shift problems. So I think your problem is more target shift. So you can look at different methods for target shift. It's not the most studied problem, but there is still a few papers doing that.
Other questions? Yeah.
What if your target data is actually a composition of different domains, not one different domain?
So only the targets are...
Yes, like target data is like different unknown domains
so
with different shifts.
With different shifts. So if you're working... So you have some domain adaptation methods that call multi-source or multi-target problem. So either you can, okay, I have one target and we just want to deal with only one target. So you do, if you have, for example, 10 target domains, you can do 10 training, like 10 adaptation. So it's a bit long if you want to be sure to work. It really depends if you have computing resources and computing time that you can put. Otherwise, you can create a big target domain with all these domains, but like the shift will be bigger. So you have multiple shifts. So maybe it will not very specific for each shift. And I think because I don't see like one method, it's more like methods are dealing more with multi-source problem. So you have multiple domains in the training datasets, and then you can adapt to only one domain. So because in your case you have different, possibly different target domains, or
Yeah, it's not a real use case.
Yeah,
it's just my
it is,
imagination.
I think it's not like you have more like the other case, like you have multi-source domains accessible, and you want to adapt to one target domain, and otherwise what we did, because in our case, in my study, we have this use case where we have multiple source domain and multiple target domain. So we have subject basically in medical classification. And so what we did is more like test time domain adaptation. So we train a classifier that is good for all the shifts. And so it will work on all the shift possible. Basically, it's more like that we are doing, but it's all another case again.
Thank you.
We can thank our speaker again. Thank